Hello, welcome, bienvenue, willkommen, welcome today on this broadcast on the occasion of the International Day of Women and Girls in Science. So for this occasion, we decided to highlight 4 Belgian top scientists who work related to space. And who are we? We are EZERO Belgium. EZERO is an initiative of the European Space Agency, and it is funded by the European Space Agency, or ESA, and BELSPO, the Belgian Science Policy Office. And we are a team of Belgian people who want to bring space closer to schools. We will use space contexts to bring STEM themes to the classroom. So we hope that today also people at school and teachers are following this live stream, but it is really for everyone to highlight women and girls in science. So for today, we have invited 4 scientists, and we want to present them to you. We'll bring them on the screen. Hello, there's Marie, Natalie, Amandine, and Angelique. So each of these women will tell you today about their research. We'll have a session of 1.5 hours. We'll start with Natalie and Angelique, and then we'll have Amandine and Denise, Amandine and Marie, who will tell you about their research. I would also like to briefly present the EZERO team. Thank you. So here also my colleagues, and you hear me in echo. There's a team that is hosting this event behind the scenes and who will follow up as well. Because as the scientists will speak, you can follow them online. You can also ask questions online. So both in YouTube and on Facebook, where we're live streaming, you can ask your questions in the chat. You can do that in your own language, be it German or Dutch or French or in English. And then we will select some questions to be answered by the scientists. So we really welcome you to ask your questions, and we hope that we can answer several of your questions. If any questions remain, then we will also answer them on our Facebook group for EZERO Belgium. So I suggest that we go right into the talks. And we will start with a talk by Natalie Lace. And Natalie Lace works on biotechnology in space. Natalie, the floor is yours.
Okay, thank you. I will start sharing my screen. I hope it's visible to you. Can you confirm? Hello? Hello?
Okay. We can hear, we saw your screen. Yes, it's
yes,
fine.
Okay, yeah. I will go back in this sharing. Yeah. Okay. So can you give me a sign if you hear me?
Can hear you? Yes, we hear you and we see you. Everything's fine.
Perfect.
Thank you.
Thank you. So yeah, first of all, thanks to you, the organizers, to invite me to join this session today. And so I will speak a bit about who I am and my job and the topic I'm working on microbiology and biotechnology in space, which I still find very exciting and hopefully is exciting to you as well to learn a bit more about it. Maybe first, who am I? And why am I doing this job? So I am someone who really loves nature, loves science already since I've been a kid. I like to understand how things work. I like to be creative. I like some challenges and definitely also to work in team. And that's probably which led me more or less on my path in sciences. So I went for having a master's degree in bioengineering. And later on, I did also a PhD, which oriented me really into the field of microbiology, actually soil microbiology. After my PhD, I joined the Belgian Nuclear Research Center, which is SCKCN in Mol, as a staff scientist, and I'm actually still working there after 19 years. And actually, at SCK, my trajectory into space started because there I focused on still microbiology, but in combination with radiation and space conditions. So currently, as I said, I'm still at SCK. I'm heading there the group of microbiology, which is about 20 people, and I'm also coordinating there the space research program. But work is not everything who makes what I am. So I also am happily married and have two wonderful children, and my family supports me luckily a lot in all the work related challenges I take. What is my job? What am I doing? I'm doing research. I'm working in a research institute, and specifically the team and the whole bio team at SEK is oriented towards understanding really the biological impact of radiation, which includes the radiation in space. Specifically for me, my drive, or where I'm working towards, or where I find my energy to do this job, is that I have a vision that we are able to transplant successfully microbial bioprocesses and ecosystems to space and have them working there for us, for the space travelers, efficiently while constantly exposed to space radiation. And that's maybe something, what I have to introduce. What is this radiation in space? So probably you've heard the last days, definitely a lot of the rovers that's been and orbiters that have been arriving to Mars, but there are also human missions to Mars planned. That's typically the communication of SpaceX programs. And so there is internationally indeed a big drive, and not only to go back to the moon, but also with the vision of going to Mars. I'm more interested in the human missions. And we study, okay, how can we transport? What kind of habitat do we need there? But also, and I put it a bit bigger, the supplies that we need there. So the food, the oxygen, the water, and that's specifically where we are focusing on. But in SEK, other people are also studying the impact on the human body. And definitely, we all know for all three of these topics that ionizing radiation in space is one of the big challenges, and even at certain points, showstoppers for certain missions. So radiation in space is higher and of those, but also different in composition. At the bottom, you see that on Earth we have about 1 millisievert per year, but once you go in space to Mars, this can quickly become 100 times, even 1,000 times higher. And this definitely has an impact on materials, but also biology. As I said, space is a very hostile environment. No air, no water, no food. So whenever we send people there, we have to provide them with a backpack of a lot of items so that they can survive. And here are a couple of numbers, but so it's quite a lot what we consume per day per person. We are not always aware of that here on Earth, but in space it becomes very clear and critical. When we think to Moon and Mars missions, these amounts only become bigger, and that's only for one person. To Mars, we will never send probably one astronaut, but a team of astronauts. So there are international programs for long-term manned missions that we develop what is called Advanced Regenerative Life Support Systems. It's a difficult name, but it's actually a very compact installation system machine that can produce in space oxygen, water, and food by actually reusing waste. We believe that biology, and specifically also microbiology, plays a very important role in these systems, and we work with that with the European Space Agency on a program which is also called MELISA, which you can Google and you will find some more information on that. The whole aim of MELISA is that we, on the left side of the screen, you will see green block, which is actually the food and the water and the oxygen we want to produce for the crew. But we need fertilizers to grow food, to grow plants, and that's where we, on the right side of the scheme, actually have a number of steps where we degrade the waste and reuse those nutrients for growing food. Very simply said, we want to do a compost heap in space. We want to have also a wastewater recycling system in space, which works with microbes. So what do we do? It's not just something on paper or drawing. So there's a lot of lab tests going on. So we have a biology laboratory at SEK where we have photobioreactors, we have algae, all different types of measurement equipment. We also not only do studies on ground and in the lab, but we will prepare spaceflight experiments. So on the bottom, you see some pictures of very small packages, sometimes passive, sometimes active, which you plug in with some electricity. We send them to space through the help of the ESA program, sometimes launched from Russia, sometimes launched from America. These bacteria and packages and processes, they stay on board the International Space Station. We have some astronauts doing the lab work there on board, and then these packages come back to ground, and then we analyze them in the lab to understand how can we bring this biology and have this working in space, and do we still have the same quality and productivity. We sometimes are very excited, and I think that's part of my job, is that you work towards some achievements. And one of those, which I am very proud of, is that 2 years ago we have the launch of this very small bioreactor in space, which we had running actively in space, which worked, and we had CO2 production, CO2 removal, which I found a very boost in achievements and keeps you going in the job. So it seems indeed there's a lot of lab work, and that's a bit the environment in which I work. But however, over the years, I'm not so much in the lab, to be honest, because we are working on large projects, and this means there is a lot of traveling, meetings, desk work, reports, papers. And this is just a picture of me in such meetings. So that's definitely probably 80% of my job besides the lab work. But I like it. It gives me a teamwork. You are part of a bigger international project. You get to learn different cultures, different people, which I think is very exciting. The last part that I want to mention is that at SEK we are a research center. We are not an academic institute, so I have no teaching job obligations like a professor, but we do have actually a very active student program. We have an SEK Academy where we welcome and host a lot of students of all different levels. It can be for hip starters of the last secondary school years to bachelor, masters, PhDs. We have summer school programs, so 2-week programs at SEK, etc. And I really enjoy also this, the interaction with the younger students with different ideas, new ideas. So if you're interested, just have a look on the Academy website. So yeah, that's me. Very short, very brief introduction, but if you have any comments or any questions, I'm always open to answer. And you can find me on my mail address or through the SEK website, or maybe even through eZero as well. So I will stop sharing my screen at this point.
Okay, thank you very much, Natalie. Also for taking time out of your busy schedule, because you are a very busy woman. Actually, all the scientists here present today, it was not so easy to get the ideal time. So, but thank you so much. Very interesting work. Questions, people in the chats, both on Facebook and on YouTube, feel free to ask questions. I have one already, because the SCK Academy sounds like a very interesting project for teachers and for their students, and we might have students listening. So can you give some examples of projects that students have done in the past years?
Yes, definitely. So for teachers and high school, we have a lot of visits, but unfortunately, due to Corona, all of this is on hold. But we, of course, want to start that again. And they can come an afternoon, visit the labs, have some information, see, touch some things. But then really for kind of project works, people can come for a couple of weeks or to join actually some of the research projects. So they will get a mentor from one of our members of the team, and they can follow one of the projects and the research and the experiments that we do. For master thesis, that's a bit more independent, so they have to develop their own project, but it's typically embedded in one of the space project or the other projects we have at SEK. But definitely you can contact SEK Academy, and we have a responsible dealing with all the requests, and we try to tailor to what they ask. Yeah, but for Corona, unfortunately, all the student projects are currently on hold, so we cannot host them for this academic year, but hopefully soon again. Yeah.
Okay, yeah, thank you very much. That sounds very interesting. Meanwhile, I think there are questions, so I would like to ask my EZERO colleagues, Maite and Peter, to join us on the screen here, and then we can go to the questions.
We have some questions here, Katrien.
Yeah, okay.
Yes, there is one about microorganisms. Natalie, have you ever been able to research microorganisms from space? And is there a big difference between microorganisms on Earth and those one from space?
Yeah, so most of our packages is where we send earthly bacteria to space, and we see how they adapt with the microgravity conditions or the radiation, which is there. There are some effects, but there's a lot of scientific literature on that and the causes and the way. But what I can say is that in some conditions, microbes grow better, grow faster. They produce also some other products which they don't necessarily produce on Earth, as well as they communicate different. So bacteria may be a surprise, but they have also chemical signals they send to each other and to react in groups or not, make biofilms, etc. And also this communication sometimes due to microgravity effects where you have no sedimentation or no convection, no mixing, so everything is diffusion limited. These things happen differently. Yeah.
And then there's another one coming from the Flemish community. Do you think more should be done not only for women in science, but also for youth and for low economy countries?
I think we should welcome any different visions and different ideas, and definitely in the space sector, it's quite innovative. It's quite out of the box thinking for solutions. And so, yeah, we feel that working with young people who had a different academic traject than me, myself, they learned different software packages, different concepts, that it's very enriching to open really your research and your thinking to maybe new ideas and new thinking. So definitely like workshop integrating really early on students in your projects, I find it personally very rewarding. Yeah.
Maite, maybe you can
Yes, okay, we have another question here. Which impact do you think the ionizing radiation of Mars has on our human bodies?
Very good question. I'm not a specialist, but I actually have in SEK a colleague, Dr. Sarah Batu, who is specialized really on human biology in space. And indeed, there is some impact that we study. Some impact typically on the immune system, also on the, so it's how you deal with infections, but also on what we call the cardiovascular system, so the blood system and the fluid shifts you have in your body under microgravity, in combination with radiation, which is more how do you call it, an oxidant attack on your body. So there are clearly some impact, and to be honest, it's one of the biggest challenges for long-term human travel in space. So for microgravity, there are a lot of what we call countermeasures. So they can run on treadmills, they can do exercises, but for radiation, there is at the moment actually no countermeasure. You cannot protect. So radiation hit the spaceship, goes through, and still attacks your body. So there's a lot to be done to develop countermeasures to know what's the impact, how we can protect, how we can therapeutically treat these impacts or effects. And there's a lot going on there. Yeah.
The next question was actually the same. So we already treated this one. So maybe I could add another one, if you don't mind. I was wondering, Natalie, if you would have the possibility to travel into space yourself, maybe to the moon or to Mars, would you like to do it? And if not, what scares you?
Very good question. And maybe 10 years ago, when my oldest daughter was not yet there, I would directly answer yes. But over time, your priorities or your interest or worries shift also a bit. So you're a mother, you're a wife, and then you think the risks you take is not only for yourself, but for the whole family, because it is and stays a risky job to be an astronaut. You know, it has an impact on your health. Is it lethal to go now? No, but does it have an impact? Yes. So when I think they would hand me the ticket, I would probably take it. But it's a bit a different shift in if I would go and if I would take the risks, yes or no, to be honest.
Yeah, fully understand. Thank you very much. Thank you. Great questions also from the public attending. If you have some more questions for Natalie has a very busy schedule. She will be here with us for a little longer, so you can post your question in the chat. But since we ended now on the tone of space travel for humans, I suggest we go over to the next presentation. So thanks again, Natalie, for joining us.
You're
We'll call you
welcome.
back before you have to go to say goodbye. And then thanks so much.
Okay.
We'll call Angelique on the stage, Angelique Van Ombergen. She is precisely doing research on human bodies in space. Am I right, Angelique?
Yes, that's correct indeed. Yeah, so I did research myself, and currently I'm coordinating the research that ESA does, let's say, on the human aspects to prepare astronauts for future missions, and also to get a better understanding of what exactly happens with the human body when you go into space.
Fantastic. Yes. So we would love to hear more about that. So
Okay.
we'd like to give you the floor for your presentation.
Thank you very much. I will share my my screen. Can somebody confirm that you can see the slides?
We can see it. Yeah.
Okay, good. So hi, good afternoon, everyone. And first of all, thank you to ESERO Belgium for inviting me to present here today. And I would say happy International Day of Women and Girls in Science. It's a day that I value very much, of course, being a female scientist myself. And I think it's a good day to put some more attention into some of the great things that some of my female colleagues are also doing. So first of all, nice to meet you. Unfortunately, it is virtually, but I think we're already getting used to that format a little bit now. Nevertheless, I'm still very happy to be here and to give you a little bit of background to what I did in the previous years and what I'm currently doing at the European Space Agency. So just very briefly, myself, I was always already very passionate about science, even when I was a little kid. So for me, a career in science myself was something that was, let's say, very logical and natural. And I studied, in particular, what I really liked to study was the interaction with humans and really, let's say, the human perspective of things. So not only science in the bigger word, but really also in regards what happens to humans. So I did a PhD at the University of Antwerp in medical sciences, and the focus of my PhD was to understand how the human brain adapts to specific environments. So one specific aspect that I studied was how the human brain adapts to vestibular diseases, so patients who have balance disorders, so disorders of the vestibular system, dizziness, postural imbalance, and so on. But in particular, I also focused on how the human brain adapts to space flights. And for that, of course, I was testing European astronauts and also Russian cosmonauts in Moscow. So this was, of course, very interesting. And this was actually my first step, let's say, in anything related to aerospace medicine. This was also what eventually brought me to ESA in the end. So what we did was we studied in particular the brain by doing brain scans before and after space flights. And by comparing those, we were able to get, and still getting, because the project is still ongoing, to get a better insight into how the human brain really changes in space and whether this change is reversible or whether it stays like that for a longer period of time. And in particular, also what the impact for an astronaut is. And I always find that important to underline that it's not because you see a certain change that it necessarily also means that that change has an implication or that it will impact their performance, let's say. So I'm currently still affiliated at the University of Antwerp as a guest professor. So I'm guiding some students there and still teaching a little bit, which I find very nice to still be able to do, because I think my heart is, of course, still also at the university for a part. But 2 years ago, I lost my heart also at the European Space Agency. So I started working there at the beginning of 2019, and I'm still working there, and I really enjoy the job very much. And I'm working as a science coordinator, which means that I'm coordinating all the science that we do on humans. So, of course, as Natalie also already mentioned, the space environment is a very hostile environment for human beings to be in. So as soon as you send astronauts to space for a longer period of time, you know that it's going to have an impact on their body. So of course, we need to study that, because only by studying it, we can fully understand what the impact is of space flights. And if we know what the impact is, then we can also try to develop countermeasures, which are methods that we can, let's say, implement to try and counteract some of the disadvantages of spaceflight. For example, if muscle and bone will become weaker, then we can try to do exercise to make them stronger again. We can give certain supplements, nutritional supplements, for example. We can put people on a centrifuge and rotate them to give them artificial gravity. And there's really a lot of combinations that we can do to try and support the astronauts, to keep them as healthy as possible, and also to have them return as healthy as possible. And that is, of course, very important. So just very briefly, when we consider human spaceflight purely from the human perspective, there are 3 big risks. And of course, at ESA, we also, we take that into account very much, because that's also why we set up certain research programs to try and get a better understanding of these risks. So there's space radiation, which Natalie has already, let's say, elaborated on. So I'm not going to go into detail on this one. But at ESA, we of course know that space radiation can be very critical, especially when we're considering of going back to the moon and eventually also to Mars. So we know that we need to get a better understanding of what exactly happens and how we can try to minimize it. Of course, we also have partial and microgravity in space, and we have a lot of understanding already from the past years on research aboard the ISS on how that impacts, let's say, certain organ systems in our body, for example, the heart, the muscle and bone, the brain, the eye, and so on. So, of course, it is very important to understand. And then the last aspect, and this will also become very important when we consider, for example, a mission to Mars, which will be very long, is the stress that people experience. So also how they do psychologically, what with their mental health, how are they feeling, what does the isolation and confinement do to them and their mental well-being? How do they function in a team, for example? Because this is all going to be very important when we send humans into space, for example, to Mars. So these 3 risks also define a little bit the research program at ESA, and we have several, let's say, platforms where we do studies into these different aspects. And of course, we have a large human research program on the International Space Station, which allows us to, of course, test astronauts. And yeah, this is, of course, the best example that we can get to eventually prepare also for future missions. So we do, let's say, research on the heart, we do research on the immune system, on muscle and bone, on the brain. We have a look at the nutrition of the astronauts, we have a look at the lungs, and so on. So there's really a very big, let's say, field of things that we do research on the ISS. But one of the issues of ISS research is that it's very costly. We only have small groups because, of course, we do not have a lot of astronauts going to the ISS regularly. So it can sometimes take very long for a study to be finished. And of course, from a biomedical point of view, we always want as many participants as possible. And of course, ISS has a certain limitation there as well. So not only do we do research aboard the ISS, we also do research here on Earth to try and draw lessons that are valuable for spaceflight and that also, let's say, hold a certain value for example, patients here on Earth. And I just want to give you a few examples of this. So what you can see in this image is a Bedrest study. And this is literally, the name already says it, we put people into bed for a very long time, usually 60 days, so 2 months on end. So we keep them in the bed, they do everything there, they eat, they sleep, they wash themselves in this position, they never get out of the bed unless it's for an experiment. And this allows us to test some of the changes that we know also occur into space. But by doing it on Earth, we of course can test more people, the study is much shorter, and we have more capabilities with regards to, for example, testing equipment, which is sometimes hard to get onto the ISS or in some cases even impossible. So ESA is focusing in particular also on these kinds of studies because this allows us to, on a shorter amount of time and with let's say, fewer money, try and get a better understanding. And of course, it also allows us to test some of these countermeasures. And in a third phase, and we also value this, we can draw important lessons, for example, for patients on Earth. And in this case, we can think of immobile people, elderly people, people who have a long-term sickness and need to stay in bed for a very long time. And of course, this is also important then to feed into. Another example is not a bed, but a bathtub, which you can see here. And there we put people in a sort of, plastic fabric. So they say dry, but they are actually in, let's say, a bathtub with specific water in. And also this allows to induce some changes in the human body, which look very much like what astronauts experience in space. And also this, of course, can help us to get a better understanding of what exactly happens to the human body in space and to draw, again, valuable lessons from this. We can test countermeasures, for example, artificial gravity, where we test people on a centrifuge and we spin them around for a certain amount of time. We have parabolic flights, which is, let's say, the only means we have here on Earth to test in actual microgravity for humans. So a lot of biomedical research is also done on the parabolic flights, and also astronauts, for example, train on parabolic flights for certain tasks to get used to also the microgravity. And then we also have something that looks more at the mental well-being, let's say, of astronauts, and we do certain isolation studies, which means that we can isolate people. For example, here in this example, this is a facility that is built in Moscow, and it allows us to isolate people for a long period of time. For example, 8 months or 1 year. We put a crew in there for with 6 people for 8 months or 1 year, and they simulate that they're on a mission, on a space mission. And of course, this is also very valuable to us to draw lessons on. And we also have real-time, high-fidelity environments, for example, Antarctica, where we have stations where crews go, and where we can also test some of the aspects on how they cope with that biomedically, but also psychologically, because this also gives us a very good input on how astronauts will react. Lastly, I wanted to mention that I'm also doing quite a lot of science communication, because I really enjoy, let's say, translating sometimes complex science findings to a larger audience. And yeah, in the last few years, I've written a few books, in particular 2 children books also on the brain and space. So if you have an interest, feel free to have a look at that. And with that, I would like to end my presentation. Feel free to ask any questions right now, or to drop me a line later on, and you have my email address as well here. Thank you very much.
Thank you so much, Angelique. That is hugely interesting. I see that there are many questions coming already, so I ask Peter and Maite to join us here on the broadcast. Thank you.
I have 6 questions at the moment.
Okay, great.
I have to select one. Maybe Maite, you can select one, and then I select one until time is run out.
Okay.
Or you want me to start?
No, just select one.
Shall I start, Maite?
Yes, please.
Okay. Well, there was a question from someone of the team here. You speak only about risk. Is there some positive aspect on going into space for the human health?
That's a good question. I think in general, people are very capable of adapting to extreme environments, and that's also what we see in space. So, of course, you need to adapt when you come into a new environment, and that is also what we see in astronauts. A lot of the changes that we see are actually wanted changes, because of course they need to adapt to this new environment where they will stay for 6 months or a year, or sometimes even longer. However, some of the changes that we see are wanted in space, but not wanted on Earth. And this is, of course, also something that is important to take into account. Of course, we need to prepare the astronauts as good as possible before they go into space. And when they are in space, we need to support them. But we also need to make sure that when they come back, that they can rehabilitate and go back to a level that is acceptable to function here on Earth. So just to shortcut the question, I would say that some of the changes are beneficial, but of course it depends whether you consider it from the aspect of space or from the aspect of returning to Earth.
Okay.
Okay, I have a question here also. So somebody asked, what's the best body type for traveling in space? Is it better to be tall or so? I don't know.
That's a good question. I don't know if there's any research been done on that. Of course, the taller you are, now with the new, let's say, vehicles of SpaceX, they have much more comfort. But I don't know if you are familiar with how a Soyuz looks like, but it's very small and cramped. So if you have to put a crew in there, I think it would be better if you were smaller. I don't think there is a specific best body type. Of course, there are certain restrictions that you need to take into account when you have very tall people, for example, that could give some issues. Same with weight, I would say, but I think there is not a specific best kind of fit. Of course, everything is very individualized. So if you know that a certain astronaut is flying, then everything gets fit perfectly for that astronaut.
Okay. Angelique, there are quite some questions about the future of humans into space, about living on another planet. Would it be possible? And maybe I would like to add to that, do you believe that within 10 or 20 years, we will actually travel to Mars as the first planet to colonize? And are we close to solutions of these big challenges, you think?
So I think on the very short and midterm, of course, the first step is going back to the moon, and this is also planned. So Gateway is in full, let's say, preparation. So we will bring humans, let's say, in orbit around the moon, and eventually we'll go back to the lunar surface. This will happen, I think, within the next few years. So it is still foreseen to have the first Gateway mission in 2024. I think that is a little bit ambitious, but okay, in any case, it will be in this decade, let's say. Then we will go back to the lunar surface, and those will be also important lessons, I think, to eventually prepare to go to Mars. But I have to say that I am convinced that at some point we will go to Mars, and that we will also stay there for a longer period of time. The question will just be when. And if you ask me, but I think that is my science background, I think we need to do it when we have sufficient answers to some of the scientific questions that are still open, in order to do it in an ethical way also for the astronauts that would be going there.
Okay, we have someone here also asking how many planets exist that can replace Earth.
That's a very good question, and I don't think I am the suited person to answer that, because that is not, let's say, my expertise. Although I think that there currently is no planet that would be able to replace Earth, and I think that's also why it's important that we take as good care as we can of the planet that we're currently on.
Exactly.
Thank you.
Yes. So we are finding planets around other stars. To date, we have found about 4,000 exoplanets, planets circling other stars. And of these, a fraction might be what we call habitable. So they might have liquid water as we have here on Earth. But then again, even if they have the temperature to have liquid water, we don't know if they have it. That's very hard to figure out. And also there might be other conditions that are very hostile to life. So your point, Angelique, is exactly the point that comes out of astrobiology. Fact is, we have a very good planet, and that's why we are here. And we better take care of it, because even going to Mars is so dangerous, and Mars is considered a habitable planet for astrophysics, astrobiology. So there's not many. And even if we find them, getting there is another issue. So, yeah. I have a question for you, Angelique, if I may. Would you, same question as we asked to Natalie, would you take the ticket?
Yes, I think so. It depends a little bit on what the destination would be, but if it would be the ISS or the moon, I think I would take it. And of course, there's an ESA astronaut selection coming up very soon, so I think a lot of people will be asking themselves that question, whether they want to take a ticket or at least try to take a ticket. So yeah, it's also something to consider, I guess.
Absolutely. Yes, exactly. So for everyone listening, there is actually a new selection coming up. If you take, I hope Angelique will also run for it. But I think it would be great to have a Belgian woman in space, actually. We have 2 Belgian astronauts, but no woman astronauts yet.
There are many more questions, Katrien.
Yes, so I see that this is a great topic. The thing is that we have to keep an eye on the time. So let's do one more question, and then we will have to say goodbye to this part of the talk, and also say goodbye to Natalie, who's going. So let's do one more.
Well, there are many good questions, but I'll take this one. Are there any other things you want to achieve this year or years to come, or a few topics where you want to pay more attention to? So it's
Is
for
it
you personally,
for
Angelique.
me personally? Okay. Well, what I think is important, and that is really something that makes this day maybe even more relevant, but I think what we see in space is that a lot of the knowledge that we have is based on male astronauts, because of course we had a lot of male astronauts, and we are really trying to be more conscious of that. Also at ESA, for example, our future study will be focusing on dry immersion, will only be with females, because we really need to get a better understanding of how different individuals, and then I'm not only talking about gender, but also ethnicity, age, and so on, how, let's say, diversity of an audience impacts how they react to space. And I think this is an important lesson then that, of course, can not only be related to space, but just in general, that to keep, let's say, the scope as wide as possible. And as Natalie also already mentioned, to have a diverse team and multidisciplinary approach with people with different backgrounds, and yeah, I think that is really important. And this is something that I myself want to definitely also focus on in the future, to try and contribute that also to the ESA program.
Thank you.
Thank you very much. We see that there's many questions for Angelique. So what we will do is we collect all these questions and we will answer them on the Facebook page of Isero Belgium. So Angelique, if it's okay with you, we will contact you with the questions that there are. And some of them can actually be grouped so that we can formulate the answers, so you can find them after the live stream there.
Yeah. Okay,
thank you so much, Angelique, for this very interesting presentation. I'd like to call Natalie on as well, because we are going to say goodbye to both of you. I think you both have meetings to go to soon, so you might not be back on the broadcast. So again, thank you so much for joining us today and for sharing your knowledge and your experiences in science. And we hope to meet you again soon and to interact with you.
You're welcome. Okay,
yes,
bye-bye.
Thank you so much for having us. Bye-bye.
Bye-bye. Thank you. So that brings us, we're now halfway our broadcast, and that brings us to the second part. And we will now go and look at satellites. And I would love to call on stage Amandine. Amandine. Hi, welcome, bienvenue. You are an expert in satellites, satellites in various systems. So we would like to hear more about that. I'd like to give you the floor.
Thank you. Let me share my screen.
Yes.
There it is. Good afternoon, everyone. Thank you for the introduction and for organizing this nice event. I'm really happy to be here today with you to share a bit of what I'm doing. So I graduated from the University of Liège in 2007, and I've been working on nanosatellites in them. And I've been often asked, what are you doing? And even more, what does an engineer do? What does an aerospace engineer do? So that's the question I would like to answer with you today, or at least give you a bit in a little overview. And I would like also to highlight other space jobs, because you don't need to be an engineer or you don't need to go to university to work with space or in space. And I will just illustrate these questions and the answers following the life cycle of Kármán, which is a tiny satellite. I will tell you more about it. So what does an engineer do? He or she takes up challenges. The basic is there. We want to solve problems. We want to find solutions. We like challenges. So we start from a question and we find a way to answer it based on science and technology and based on what we learned. So the question behind Kármán was what happens when a satellite re-enters the atmosphere. So you can see there a picture of a satellite re-entry. And okay, scientists, professors at the Institute wanted to know more about that, how the materials behave, and how to do so that it generates not much debris or as little debris as possible. So they wanted to know more about that, and also they wanted to know if they could do it with a CubeSat. I mean, that's even a bigger challenge. Let's do it with a tiny satellite. So a CubeSat is basically a satellite of that size. That's the basic 1 unit CubeSat. It's 10 centimeter here, so the volume is 1 liter. It would weigh about 1 kilogram, 1.5 kilogram. Luckily, you can assemble them, so you could have a bigger CubeSat. And for Kármán, they wanted to do like something like 3 units. So it will be 30 centimeters, 10 by 10. And that was the initial challenge behind Kármán. Let's do Kármán, the VKI re-entry CubeSat. So our aerospace engineer want to solve problems and imagine solutions. 4 main problems or 4 main challenges for Kármán. First, we have to slow down a bit. When the satellite is in orbit around the Earth, it's about 25,000 kilometers per hour. And we want to slow it down. In the end, it will be 0. Then second challenge is about the thermal aspect. When the satellite will re-enter the atmosphere because of the shock wave, the temperature will increase a lot, a few thousands of degrees. So we need our satellite to survive that, because that's the part that we are interested in. We want to take measurements during this re-entry, so we need it to survive during the re-entry. Then third challenge is the size. And you see there with Thomas Pesquet, the IXV vehicle. It's a big spacecraft used for re-entry experiment. Okay, we want to do more or less the same at a smaller scale. So we need to fit everything that's there into something the size of a shoebox. That's our third challenge. And the fourth challenge there with ET is that Kármán should be able to call home. So it will be collecting data during the re-entry, but during the re-entry, it cannot communicate because the radio waves are blocked by the plasma, by the ions. So we should find a way to communicate after the re-entry. So with all these 4 challenges, engineers and my former colleagues worked a lot to design Kármán. And there you can see the design of Kármán. So to face the heat challenge, we have a thermal protection here in cork. Yes, the same cork as for a bottle of wine, for example, and a really insulated survival unit that with everything that needs to survive during re-entry. To slow down, we have deployable solar panels that will slow down a bit so that we can earlier re-enter the Earth. Then for the size challenge, you can see that it was really tricky to put everything inside this volume. And finally, for calling home, we have a dedicated radio system so that we can communicate over the Iridium network, which is a satellite network that gives communication possibility all around the world. So that I will keep it very short because I don't have much time, and I would like to give you an overview of the entire life of Kármán. So that was the design. And which kind of space job do we have here? We have engineers, mission analysts, thermicists, computer scientists, because we need software to run on board the satellite, researchers, draftswomen and draftmen to do the drawing and prepare everything, people working on the workshop to prepare everything. And when the design is done, well, it's more an iterative process, but you build and integrate your satellite. And finally, you manage to have it work. So a few pictures during Kármán's life. Again, many professionals can be involved there, technicians, field engineer. Two examples, watchmaker, you can see on the right, my colleague Terence, is by he studied as a fine mechanics and watchmaking studies. So his very precise skills are very appreciated to integrate satellites. And about dressmaker, Thales Alenia Space, a space company, working here in Belgium, but also in France, they were really looking for dressmakers, couturières, because they have really good skills to assemble the electronics. So that's really a profile that they are looking for, because they need very, very accurate people. Then you have your satellite. You need, of course, to test it to be sure that it will be working properly in space. 2 examples of tests that we do. On the left, vibration testing. So you shake your satellite inside of a box so that you see some vibration which are similar to what they will see in the launcher to be sure that your satellite will still work after the launch. And on the right, you have thermal vacuum cycling. So you put your satellite in a vacuum chamber and you go for up and down in temperature, so hot and cold cycle to make sure that your satellite can survive in the thermal environment of space. You test, so you need facility technician and engineers, test engineers, and sometimes it doesn't go as planned. So there the engineer has to analyze the data and solve problems again. An example is doing the first vibration campaign of Kármán. The structure broke, you can see on the first picture, and the wires that are holding the panels folded during the launch also were cut. So there was a redesign, we had to change materials, and their engineers had again to find solution to new problems. Keeping the story short, that's also the occasion to introduce responsible for product and quality assurance, which is very important in space, where you have to make sure that everything is produced according to the plan and that everything will work from first time. Then finally, you can have it launch. How do you launch a CubeSat? You put it in a deployer, which is basically a box. You slide it into it, you close the front door, and in the back you have a spring that will deploy and push the satellite into space when it is time. You can put this deployer directly on a launcher, but for our case, it went first through the ISS, so it was launched in the Cygnus cargo spacecraft on top of on a Falcon 9 rocket. Then the cargo docked to the ISS, and there Kármán has been waiting in his box for a few weeks on board, and finally it was deployed. Of course, be sure not to be illegal. There are some regulatory rules to respect, some laws to respect. Your satellite needs to be registered, your operation needs to be authorized by Belgian state. Also, you would need to have your radio frequency coordinated and allowed. So there is place for space lawyers and all kinds of officials. Finally, Kármán is deployed into space. It was nearly 1 year ago. And you can see there Kármán getting out of the box. So the box is manipulated by the robotic arm of the space station, and then Kármán can go out and start his orbital life. There you have astronauts involved. We already talked a lot about them, but also operations support on ground, which are very, very important, but also journalists and space journalists, because on such a nice event, of course, we want everybody to know about it. And then Kármán starts his orbital life. So you want to communicate with it, you want to operate. These are the antennas we have on top of the VKI ground station, which that we can communicate with Kármán. And there you can also see how we track Kármán. So we have a software that gives Kármán position all over the time. And when it is going over VKI, we can communicate with it. So Kármán is sending us data about its status, and we can send comments to Kármán. There you have space for radio operators, mission controllers, scientists. And then again and again, engineers will like to solve problems. So what happened to Kármán? There I show you real data that we collected from Kármán, and you can see all along Kármán's life, so from February on, the temperature data. In blue, the temperature of the onboard computer, in orange, the temperature of the radio, and you can see that the data stopped at some point in July, and that the temperature was increasing. So again, we analyzed data to understand, and we saw that Kármán, it was not expected that it would undergo a full sunlight for 4 days at that time in July. So typically it should be 1 hour in sunlight, 30 minutes in the shadow, and there it was full sunlight for 4 days. So we understood our mistake, or the error at least. And so what do? You learn and you try again. And now we are analyzing Kármán and especially the thermal behavior of Kármán, so simulating. That also an important part of an engineer job. You would simulate because you cannot always test. And we are trying to understand what went wrong with Kármán to see what we could do to improve it and maybe try again, hopefully. So that's it for me. That was a short version of Kármán's story. I wanted to show you, first that you understand better what I do and what aerospace engineer can do. Also, if you're working on a small satellite like Kármán, you would do a bit of everything. But if you are working on larger, bigger mission and bigger satellites, you will get more specialized on a topic and working with a bigger team. And one important side of my message was also that there are many, many jobs related to space, and that's not only for engineers, that's not only for researchers. So if you like space, well, you might really well find a way to work with space in your career. And that's it from me. I would be happy with any question.
Thank you so much, Amandine. There are many questions. Actually, the questions are streaming in. So I think Peter and Maite might already have some questions in mind. I just want to ask briefly, as they pick their questions, what made you get into this research?
I think when I was younger, very younger, like 8-year-old, I wanted to be an astronaut. Then, at school, I liked mathematics and science. I like to find solutions to problems, and space is really an exciting topic. And so first I worked on a smaller CubeSat at the University of Liège, and then I had the opportunity to join the VKI team on another CubeSats project. So that's really nice because you have the opportunity to work on a mission from the beginning, from the first idea until the end and until the results. And that's not always the case when you work on bigger mission. You will work on a small part of it because it will take so long from the first idea to the result that it's difficult to see it from beginning to the end. And with CubeSats, you can really see the entire life of your satellite.
Exactly. Thank you so much. Thank you.
You're welcome.
Peter or Maite? There's so many good questions, so please.
Yes, maybe here I have a question. Since you learn so much of your mistakes, the question is: did many things go wrong during testing? Have you had several failed launch of satellites?
Yeah, of course, during testing, many things can go wrong. That's why you test, but also many things go right. And of course, you may be tempted to focus more on the failures, but yeah, we had some failures, of course, and we learned. And also at some point, the radio was not working, or at some point, you find that another piece is broke over the night. But there are also many things that improve, and especially with CubeSat, you will start to work and to test very early in the project, because that's how you will learn and how you will build a really reliable CubeSat. And everything that's good if you have failure, because everything that fails on Earth, you will know it, and it won't fail in space, because you met the failure once and you will solve it. So that's really the purpose of test, to have failures now and here on ground where we can fix it. If it don't fail on Earth and it fail in space, there is no way you can go up there and fix it.
Thank you.
But the launching itself did not fail, no.
Okay. We had a question about that, actually, if a satellite, try to find it out, but if a satellite goes in the wrong direction or so, can you correct it? When it's in space.
To some extent, yes, but we cannot dramatically change the orbit. So for Kármán, it's a small satellite, we don't have propulsion. So we won't be able to change really the orbit. We can control the attitude. The attitude is the way the satellite is oriented along the orbit, where it is looking to. That we can control, but we don't have propulsion. Also, bigger satellite can control the orbit, yes, but usually that's the rocket job and also the deployer job to put you on the right orbit, and then thanks to the physics law, I mean, you would stay there because of the gravity, because of your initial velocity, you will follow your orbit. So if you are from the beginning on the right orbit, you will remain there and go down really slowly until you re-enter.
Thank you.
There is one about your employer, the Von Karman Institute. What does it do exactly? What is the research that VKI is doing in general?
So VKI is a research center, but also an education center. So we do research through education and the education through research. We are mainly focusing on fluid dynamics. And we are also training students, so master after master and PhD in fluid dynamics, all aspects, all speeds. We have a lot of wind tunnels so that we can test things at very, very different speeds, very high speeds or lower speeds. So we study everything related with the way that the fluids are moving. It could be the air or it could be liquids. So that's very, very broad.
Now, some people are interested about the coding. Was it hard to do the coding, the programming of the Von Karman satellite?
Yeah, that's not easy. That's really a difficult part, and that's why we did not do it ourselves. We were working with a UK company called Bright Ascension. They developed the software for us because it can be very specific. You need something very robust. You need to think about everything. It's really a specific job. But we tested it. So for days and even for months, you test everything, every case. You simulate everything you want to do with your satellite, and you want to test it and be sure that the satellite reacts the way you want it to react. So yes, coding for a satellite, it's a tough topic. It's very specific, and we need very skilled people to do it. It's a specific job.
I'm looking at the time as well, but maybe one last question. There are actually many more questions in the chat. So we will also, again, take them to answer after the talk. So if it's okay with you, then we'll get in touch with you, Amandine, with the questions that are there. But there was
the last one is a good one, Catherine.
The last one? Okay.
I would take this one because it's especially for young people.
Yeah. Okay. So that's a question from Mike Touré. What can you tell to someone who's trying to look for a job in this sector? Where can you advise him or her to start? Indeed, a very good question.
I would told her or him that he will most probably find a job in space sector, because space companies are really looking for all different kind of profiles. It depends a lot of your topics, of your specialty, of your background. So it's difficult to give a general answer. But yes, there are many space companies in Belgium. It also depends on what you want to do, if you want to do more research or working on satellites. But definitely there are many opportunities in the space area. So it would be a bit easier to answer knowing the profile, but yeah. And if it is for a younger person, like what should I study? And study what you like. And if you like science, that's perfect, and study science. But if science is not your thing, that you could also be a space lawyer. Or if you like public outreach, there is also public outreach in the space sector. So first do what you like and be passionate about it, and then you will find your space job.
Thank you so much, Amandine. I think that's a nice note to end this part of the presentation on. So I want to thank you again cordially for being here and sharing your knowledge. Again, if there's questions, please ask them in the chat and we will get them to Amandine. But for now, we'll say goodbye to you, Amandine, and we'll call you back later, and we will ask Marie to join us. I'll add Marie to the stream. Hello, Marie. Welcome here today.
Thanks.
So today we've heard already about humans in space, microbiology in space, how to send things into space. But what can you actually do when you're looking from Earth at space? And that is exactly what Marie is doing, because Marie is an astrophysicist, more particularly an astrochemist. And we're very curious to hear your story. So the floor is yours. You can share your presentation.
Thank you. I have shared my screen and I started my presentation. So if there's no protest, I will just continue with my talk. So hello everyone, and thank you to the organizer for having me. I'm Marie van der Zande and I'm a scientist that studies astrochemistry. So maybe first, what is astrochemistry? So astrochemistry is a study of molecules in space, and it asks two main questions, namely which molecules are present and why, and what can these molecules tell us about what's going on over there, the density, the temperature, the physics. So how can chemistry help us better understand the physics? And as we've heard today, and as you probably already knew, space is very different from our comfortable Earth. It's very hostile for people, but also for molecules. So when the first molecules were detected in the 1930s, it actually came as quite a surprise to chemists on Earth. Because it is so hostile, the densities and the temperatures are completely different to those that we have here on Earth, from the very low range to the very high end of densities and temperatures. So astrochemistry can actually help to test the limits of chemistry. And in this way, astronomy and chemistry can nicely interact and help each other progress. So far, some 200 different types of molecules have been detected in space, and here they are, all in this table. Most of them are fairly simple, so composed of 2, 3, 4 atoms. Some of them we already know. We have carbon monoxide, water, and ammonia all floating around in space. As we go to the longer end of these molecules, there's some carbon chains popping up, and there's a clear organic footprint in the chemistry. So, for example, methanol and acetic acid, you might not find them in your house, but you can certainly buy them in a pharmacy. They're also readily available in space. But then, of course, there's these weird molecules. For example, C8H. That's 8 carbon atoms in a row, with only 1 hydrogen atom at the end. Now, if C8H would walk into a room here on Earth, it wouldn't live for a very long time because the density is quite large. There's also a bunch of water floating around in the air. It would react immediately and it would be hydrogenated. These long, bare carbon chains, that's not something you can readily find here on Earth. And it's these weird types of molecules that tell us a lot about the environment in which they live. And throughout a galaxy, you can find many environments that are rich in molecules. And these can also be called astrochemical laboratories. And they're very different from labs here on Earth, mostly because of the density and the temperature, but also because we can't go there. We can't just poke around in it, heat it up, shake things up. No, the only thing we can do is look at it using our telescopes and satellites and think about it. So that makes life more difficult, but also more easy in a way, because you can't knock things over if they're in space. That's certainly an advantage for me. Now, and throughout the life cycle of a galaxy, several of these astrochemical laboratories can be identified. The galaxy that we live in is the Milky Way, and this is a picture of the Milky Way. And the Milky Way is also constantly evolving. It's just not something that you see on a daily basis. So stars are being born and stars are dying, but it takes much longer for them to do this than an average human lifespan. So we don't really notice it, but it is going on in the background. And now, very briefly, stars are born from dense clouds of material that occupy the space between the stars. That's also called the interstellar medium. And the life and death of a star is determined by its initial mass. So massive stars that have a mass more than 8 to 10 times that of our sun, they will end their lives in a supernova explosion. And in this explosion, they will expel their outer layers back into the interstellar medium. So lots of gas, also a lot of dust. just the entire life's work of that star back into the interstellar medium. Now, our sun isn't massive enough to explode as a supernova, but it will die just much more gently. So instead of throwing everything off, it will more lose its outer layers via a calm stellar outflow or a stellar wind. So not an explosion, but more of a breeze. And again, gas, dust, entire life's work back into the interstellar medium. So the saying that we're all made out of stardust is actually true, because all the material that we are composed of and our homes are composed of was all produced by stars that have died a long time ago. And if we follow this journey from clouds all the way to a star and planets, we can determine many astrochemical labs and also use the chemistry to figure out the physics of what is going on. So we start off with an interstellar cloud, and the chemistry here is very simple. So atoms, two diatomic molecules such as carbon monoxide. That's mainly because it's very cold, and when I say very cold, I mean 10 to 100 degrees above the absolute zero temperature, so that is very cold. And there's also a very low density, so it ranges from 1 to 1 million particles per cubic centimeter. That might sound like a lot, but here in this room or in your room, there's like 10 to the power of 19 particles per cubic centimeter. So 1 million on Earth corresponds to an ultra-high vacuum. But still, chemistry can occur. As the cloud collapses under its own weight, stars is being formed, a protostar, and as the density increases in the collapse, more chemistry can happen, because as the density increases, you bump into more other particles, so longer molecules are able to form. After a while, the star is formed, but there's still a disk of material surrounding the star. This is called a protoplanetary disk, because this is the disk where planets are being formed. And again, there's much more complex chemistry going on. And in fact, the very first steps of planet formation are more of a chemical process than a physical process, because it's just particles sticking together, and then after a while you get a planet. And then finally, you end up with a star surrounded by its planets, just like our sun and our solar system. But there's many more detections of exoplanets, as Katrien has mentioned, and they all have an atmosphere that we can look at as well, using telescopes and satellites. So as we follow this path, the chemical complexity increases. We start off with very simple molecules, and we end up with quite complex chemical entities, such as our cells. And I mentioned before that even organic molecules can be found, especially in a protoplanetary disk. And one of the more exciting detections was a detection of glycine, the simplest amino acid on the surface of a comet. So a molecule essential for life on Earth was found in space, where it was formed purely in using astrochemical processes. So this then begs the question that maybe the components of life were formed in space and then seeded onto the Earth. So that's one of the more philosophical questions that astrochemistry tries to answer. Now, what do? I don't really study the origin of life. I study the chemistry around dying sun-like stars, so rather death than the origin of life. But as I mentioned before, it's these dying stars that seed the building blocks of a future generation of stars and planets. So maybe it's not the death phase, but rather the neonatal phase. Let's think about it that way. I am a part of the group led by Professor Leen de Sin at KU Leuven. I am a postdoctoral researcher there. And together with all my colleagues in Leuven and also international colleagues, because astronomy is very much an international field, we try to figure out how exactly stars like our sun die. And what's more important, well, more interesting to me, is what they exactly expel back into the interstellar medium, the gas and the dust. And we do this using both observations and theory. And here on the right, these are beautiful observations that we have made in collaboration with a huge international consortium of several dying sun-like stars. So the stars themselves are all at the center. It's like these white dots. They seem quite small, but when our sun will enter this phase, she will have swallowed the Earth. So actually these stars are quite large, and then their outflows, well, the outflow of the sun will be larger than our solar system. So these are huge systems. And as you can see, there's a large variety in what they look like. Some look a bit more fuzzy, others, this is a space rose, all very complicated. And for that, we also have to use theory to see, well, to check what is going on. And my research is theoretical chemical modeling. So my computer is my virtual lab. I run simulations or experiments, and then I compare them to observations. So why is this molecule there and not here? Why is there so much of water and so little of hydrogen cyanide? What is going on? And, you know, I try my best, but sometimes the model isn't good enough. That means that I need to improve it. So I do this by including new physics, but also by including new chemistry. And it can actually be new chemistry, because, well, astrochemistry is not only international, but also interdisciplinary. So I then asked friendlily to befriended chemists if they can please measure a certain reaction in their lab, so I can plug it into my virtual laboratory and see what effect it has on this astrochemical laboratory of dying sun-like stars. So it's international and interdisciplinary collaboration. And a day in my life actually involves a lot of programming, because that's how I communicate with my molecules. I also talk a lot with my colleagues to try to solve my problems, their problems, tackle issues from different viewpoints. But most of my close colleagues are actually international and live abroad. After enough programming, thinking, discussing, I can write up my results, and they are then hopefully published in an international journal. So that's how everybody else knows what I've been doing, and how I know what everybody else has been doing. If there's not a pandemic going on, I actually travel quite a bit. I go and visit my colleagues for work visits, or I go attend scientific conferences where I present my work and others present their work. And this is really where you meet new people, you get new ideas, you get to start new collaborations and tackle all these problems that nature keeps throwing at us from different points of view. So every day I learn new things. So even though it looks like an office job, I'm just sitting in front of a computer at a desk, it's much more interesting on the inside. So if you like learning new things, and if you're a bit stubborn, as in there's a problem and you really want to fix it and it's going to take a week, but you just want to go for it, then astronomy and astrochemistry really is something for you. If you like thinking about things that not a lot of people think about as well, that's a good trajectory for you. And how did I become one? So from a young age, I was always interested in space, and I wanted to become an astronomer. So I started with a bachelor in physics, then went on to a master in astronomy and astrophysics. And around that time, I also learned about molecules in space. I was also interested in chemistry, just not as much as in astronomy. So that seemed like a perfect plan. And I was fortunate enough to find a good PhD project with a good supervisor, so I could start and finish my PhD. That takes 4 years in Belgium, but no worries, you're paid at that point. And now I'm a full-time researcher. I'm a postdoc at a university. But this is not the only path. You can tackle it from many angles, depending on your interests. So for example, you can start with doing a bachelor in mathematics, or you can do a master in physics, computer science, engineering, and then they'll recalibrate back to astronomy, either a master's or a PhD. And of course, astrochemistry can also perfectly be tackled from the chemical point of view. So there's not just one way to become a researcher. There are many options, and it all starts with your interests. So thanks for your attention.
Thank you so much, Marie. That was super interesting. And I actually wanted to ask you, how did you become that? But you already answered the question in your slides. So that's wonderful. And meanwhile, we have great questions that have come in. So I'm going to give the word to my Ezero colleagues, Peter and Maite. to pick some questions. We will not be able to answer everything, but we will do so on our Facebook page, the Isero Belgium Facebook page. Okay.
Yeah, so first question, have you, or maybe have we, discovered molecules that aren't from our solar system? If so, do you have a clue from where they came from?
Yeah, so the molecule that I talked about, the amino acid, that's from within our solar system. It's a comet from our solar system, but all the other molecules from interstellar clouds or protoplanetary disks, that's around other stars. So we know where they come from, namely like from over there, but we can't really go and measure them because it's a bit too far away. So either we can do solar system work and then we can send a satellite, for example. It'll take some time and it takes a lot of money, of course, but all the other molecules are from still within our galaxy, but not from our solar system. And there's even actually current detections of molecules outside of our galaxy because, like physics, chemistry is universal. So astrophysics and astrochemistry, it's the same laws everywhere.
Thank you.
Heavy elements. Some heavy elements are made by humans, do not exist naturally. The question more specific is there proof for heavy elements with more than 118 protons?
Well, these heavy elements are made in supernova explosions because there's a lot of energy just floating around. It's a supernova explosion. That's where all the heavy elements are made, so most of them. And I'm not sure whether we can, well, maybe it's made for a very short time, but then we can't detect it within that short time frame. But there's no current evidence, at least, that it's made in these supernova explosions, and certainly by the time that we see it, it's gone. So that's mostly, well, people knocking things into things on Earth and then observing it for a millisecond. So maybe, but we don't know.
Okay, Maite?
Yes. How can you detect strange unknown molecules in space? How
Yes,
do you
that's a
detect
good
that?
question. Yeah, so you just do it by using light, the electromagnetic spectrum, and you do it by making use of fundamental properties of molecules, namely, well, just use a very simple molecule, CO, you have a carbon, you have an oxygen, and they can rotate around each other. And according to quantum mechanics, they can rotate around each other at very specific frequencies. So either this fast or that fast, but nothing in between. So if they're going this fast and they lose their energy, because why would you want to go this fast if you don't have to? Nature is lazy. They go down in energy level, a rotational energy level. And that then corresponds, so they lose energy, and that's being lost by emitting a photon. And that photon is emitted at longer wavelengths, so we can't see it with our eyes. It's more in the radio domain. So we put these huge satellite dishes, and then we look around and we look for these electromagnetic fingerprints of molecules, because each molecule has different rotational transitions. So from just turning around its own axis, but also vibrating. Lots of things going on a very, very small level. And then spectroscopists in the lab here on Earth, they measure it, and then we compare what they measured on Earth to what we see in space, and say like, so that's carbon monoxide, which is hydrogen cyanide. But it's again a collaboration, because without work from people in the lab here on Earth, we wouldn't be able to tell which molecules exist in space. But not the other way around. There's certain rotational transitions that we can't identify, and then you have to ask your friendly neighborhood spectroscopists if they could maybe measure rotational transitions of this very exotic molecule, please. So it's an interaction between terrestrial and astrochemistry and observations.
Thank you.
One more, Katrien? Yeah. So you've been talking about our past as stardust, but this one is about our future. When our sun becomes a red giant and swallows the first 3 planets, Will the molecules from these lost planets be returned to space one day to form a new planetary system?
Yes, so maybe not our exact composition. So we will maybe be decomposed in certain way. That's certainly something that I'm particularly interested in. So what happens to these planets? Will they be obliterated? Will they be evaporated? So instead of having a large clump, or just a large space rock, we go back to small dust particles. Maybe the gas giants, or like Mars or so, could still be rotating around the white dwarf that remains after our sun has died. The white dwarf will remain. But everything else will be returned back to space. Maybe not just like our glass, it will return back to being silicon, oxygen, hydrogen, carbon. But yeah, it's a huge regeneration and recycling cycle. So yeah, we will end up in a new generation of stars and planets, just not maybe in a form we're comfortable with.
And maybe for some perspective, Marie, when is this gonna happen?
Oh, in 4 billion years, so we have plenty of time.
Okay, so it's not worries for now.
No, not worries for now. We have more pressing issues at the moment.
Okay, thank you. Well, I think that's a very nice note to end on, the future of our solar system, because I'm keeping an eye on time. We're approaching 3 o'clock. So I would like to thank you again, Marie, very, very much for sharing your knowledge and your wisdom, and also how people can get into an exciting career as you have. And then we will also ask Amandine back on the stage if she's still around. Yes.
Sure.
So there might be a few more questions that are general. Yeah, maybe just one it was asked in relation to your talk, Marie. Do you recommend that more people go and study physics?
Well, yes, maybe. If you're interested in physics, why not? Go for it. Of course, don't do it if you're not interested, because then it's just 5 years of agony. But if you're interested in it, why not? Even if you do not end up in research, there's plenty of other professional routes for you to go into. I haven't heard of any physicist that it's without a job. So it's good for job security. If you like it and you have the opportunity, why not?
Fantastic. Yes, it actually rings a bit with what Amandine said before as well. So follow your passion, and then if you have some particular goal in mind, you might end there as well by following your passion. So do you have anything to add to this? Amandine, Marie, Peter, Maite? I see that people are thanking you for your time. So again, also from us, thank you so much for being here today. There was also, there were some pupils who were with their teacher live on the broadcast today. So that's really, really great, because that's also what we wanted to reach. So we hope to do similar broadcasts in the future, and we are very, very happy to have our first one today on the occasion of the International Day for Women and Girls in Science, because we want to encourage everyone to follow their passion in science. So with this, I would like to really thank everyone here, my colleagues in front of and behind the scene, and especially the scientists who joined us today for their time, and also importantly the people who joined us from everywhere, because there were people from Belgium in different language communities joining, but also internationally. So it's really great to have you here today. And you will find the live stream after as well, both on YouTube and Facebook. And as I said, we will answer the questions that were not answered because of time constraints on our Facebook page, ESERO Belgium. So thank you so much. Have a great rest of the day, and take good care, and see you soon. Thank you.